John, over to you.
Okay. Well, thanks for inviting me. Thank you, Colin, for trapping me at Schiphol. I'm going to run through the PowerPoint. Hopefully it's not going to put you to sleep. The simulations I'm not going to run live in the presentation, but for those of you who are interested in actually seeing how the simulations run, I'm more than happy to sit with you afterwards. I do have a separate projector which I can plug my computer into, so if there's enough people interested, I can plug the projector and we can project it onto that screen, but I didn't want to put it onto the university computer. Just a little preamble. I'm a chemical engineer by background, but specialise in instrumentation. And when I sort of semi-retired, I went to an exhibition, Eurochem, and met the ChemCAD people who do process simulators. And that's about 12 years ago. And since then, it's sort of become my hobby, if you like. I go all over the place doing courses for chem stations, and I find it fascinating as a tool for doing process design work. But I hope I get the flavour over to you tonight that with dynamic simulation, we can do things that we would have wanted to do years ago but couldn't, in terms of setting up control loops and looking at interactions between loops. So I'll kick it off. I know you're instrument engineers, but in my days on plant, I always felt it was the instrument engineer who knew more about the process and every aspect of what was going on the plant than perhaps the chemical engineers. I hope I don't upset any chemical engineers in the room, but it's the instrument engineer always seems to be the person who had to get the thing up and running when there'd been a breakdown. So you can have access to these PowerPoints if you're interested in them, but you've got the little write-up there, and I think you're probably going to post the PowerPoint on the web anyway. But that diagram is a very simple diagram of what a simulator is all about. A process takes feeds, it has recycles, it does reactions, separations, and it creates products and waste. And it also takes energy, and the process can absorb energy and discharge energy in a waste format. And the words at the bottom are the simple words describing what a process is. And at the bottom, the additional features are the heat transfer, phase equilibrium, and reaction kinetics. And that slide basically is a simple presentation of what a simulator is solving. More interestingly for us, this is sort of, my background's from Shinsky in terms of control, so I'm sort of extracting from one of Shinsky's books the basis of that slide, because he maintains that in a process you've got feeds, products and waste, energy again, and you've got dead times and capacities in various combinations, and that's it. So a dead time, from the moment you've taken action on a process, there's a fixed time delay before you see a reaction. Capacities are like filling tanks, where there's a volume involved, or there's heat transfer involved, like specific heat of solids and fluids and things like that. The simulator I work with is ChemCAD, but there are several other simulators. There's HYSYS, there's Aspen, there's various other people. The structure is you have a steady state module which sits on top of physical properties and the basic structure of the software, which is applicable to all modules. You've got the dynamics, which is what we're going to talk about, and you've got heat exchangers. So that's the basic simulator structure. And the simulator is a graphical based simulator, and what you basically have, you take from a palette various unit operations which hold the mathematics associated with a particular operation. So there's a distillation column. So it has all kinds of algorithms in there to study distillation, reactive distillation, simple vapor liquid equilibrium. You've got flash vessels, which can do flashing of liquids. You've got simple dynamic vessels. You've got relief valves. You've got pipe sections, so you can actually simulate pipes and pressure drops, heat exchangers, and these are all connected quite simply. So you come in with a feed, it gets processed, there'll be something coming out of this side here, bottoms and losses. You've got the top here, condensers, emissions to atmosphere. So it's a graphical presentation of the process. That literally takes half an hour to draw maximum, and then you have to configure it, of course. Have you worked with simulators? Most people. Yeah. I'm going to talk about connecting a simulator to a process, which is done more often in the continuous process industry as opposed to the batch industry. So you will have a SCADA system. You have an interface. There's various interfaces available now. I'll talk a little bit about the OPC interface. Within the simulator, we have a data map facility which links directly to Excel, which is very powerful. It allows you to do various data exchanges. And then you have the structure of the simulator again. So what we're really talking about here is there's the DCS system. It can be connected by DDE, dynamic data exchange, through data maps to a dynamic model. Or you can do the OPC route, which is a company called Matricon, are leaders in the field. And they'll do it through an OPC server to a dynamic model. OLE process control is what OPC stands for. OLE stands for object linking and embedding. So what you basically have, you have a simulation, which is this, and then you have a graphical interface control system. That's being built in Excel, that graphic. So doesn't look like a typical DCS graphic, but it's the same principle. So that graphic's being built in DCL and links with this model here. So you can change tuning parameters in here. We can put different control valves in of different sizes and characteristics, and we can play with different feed rates and streams. Within the simulator, we can ramp values, we can change values. So that gives you an overview of what the structure of the system is. And this interface is built in now with all DCS systems. So there's nothing fancy about that. I mentioned Matricon. They're the first people I came across, but if you have a look at that, what they're saying is they can connect your device and they can connect to all this spreadsheets, archiving reports, HMI, and then on the other side of it, more interestingly, is of course they can come onto the plant. They can get into PLCs, they can get into DCS, RTU, and it's a straight data exchange. It's much better than the DDE system. Again, another picture of the overall view. We've got sensors going through various pieces of hardware into buses, mainframe PCs, data highways. I know one client, he's actually using this technique. He has chlorine dioxide plants all over the world, and he has a guy sitting in an office in Scandinavia somewhere, and every day he goes into the office and dials into every plant to see just what's going on in terms of efficient use of energy, a very, very powerful device. I don't know who that guy is. Hope he doesn't see this picture. And there's a simulator there. Just to give you some examples, we did a project some years ago at Teesside University where we connected their distillation concrete to their oil control system using various interface modules which we built up here and connected to a PC via the Excel interface. So the double arrows are just saying there's information transferring all the way through this package. We're connected to sensors here, onto here, and we're taking that information. This is a mimic that's being built onto the PLC. We used software by Tascom. We use their software to do this. And basically what we're doing is you can compare, these are the simulator values, and these are real values. So you can build your mimic to take real data in, and your simulator is also prompting you in terms of the information that the simulator considers to be the optimum value. So it's sort of prompting the operators to where the deviations are. When I say online simulation, it doesn't necessarily mean to say we've closed the loop in terms of allowing it just to go and do the adjustments itself. But there are people who have closed the loop. So it's an online, offline situation. So we did a few runs on this, and basically what we found out, this is the column top temperature, and this was the reflux ratio. The long and short of it was we found there was insufficient lagging on the thing, and the internal reflux on the column was absolutely horrendous. So we basically recommended to relag the facility and take it from there. You've got that graph in the handout I gave you. On this particular project, the benefits we got were, we found there was a major problem with the reflux. We could actually, the thing about the simulation is you can monitor variables that you're not necessarily measuring. So now you don't have to measure everything. So, for example, we could do an online analysis of the methanol distillate concentration based on the simulation values. We didn't have to measure it online. Got temperature profiles from the prediction. We only measured temperature at about 3 points in the column, but we got a profile throughout the whole column. We could predict refresh ratios for top compositions, benefits, increased understanding of the process, and we came up with the answer about upgrading. We did a combined heat and power facility for someone. This was quite daunting when we first saw it, because what you have is gas turbines generating steam at 10 bar, and you've got another gas turbine set generating steam at 46 bar. You're going through turbine alternator from 46 to 10. You've got HP turbines doing drives, but you've also got turbines for pumps and things doing medium pressure. You've obviously got pressure letdown stations in parallel with all this. And then, but the thing is, what determined what you could do was this is going to process. And it's the process that decides how much steam you want. So you have all this equipment here which is capable of generating a bucket loads of steam, but you're limited by what the demand is. And it becomes quite a trick to optimize the use of equipment so you're not spending a lot of money on gas turbines here and supplemental fuels to do, particularly at low rates, low demand rates on plant. As we all know, many facilities now, the demand rates have gone down from original design. So it becomes very challenging to keep the economics right. So what this is about is really giving the operator advice on how to best select equipment to satisfy the process demand, which he's got no control over. To simulate the gas turbine steam generation, you have compressors, use a thing called the Gibbs reactor, got the turbine and there's the generators, use combustion chambers and there's the heat exchanger. So you have modules which you can connect all this together and simulate the actual performance of the gas turbine. You can calibrate it against the performance of the gas turbine. And that's a breakdown even further of the gas turbine setup, the calibration. The gas turbine is using fuel here, obviously, and that's generating steam. And on the waste heat boiler side of things, you might not want to run this, uneconomic to run gas turbines at low rates. So at the back end of this, you have a boiler, and you may burn supplemental fuels to the waste heat boiler. There's steam to plant. And what we're doing, based on the known characteristics of the process, we can work out what the boiler feed water flow rate, what the steam flow rate would be for a given fuel consumption. So what we're saying here is the steam production is a constant, which could be variable, it doesn't have to be linear, times the natural gas to the gas turbine, plus another non-linear constant, natural gas to the supplemental, to the combustion chamber here. It gives you an idea of costs and how the operator with wrong choice could cost a lot of money. Conventional boiler, which they do use as backup when they don't want to run the gas turbines, you're talking, this is euros per tonne, say €1 per tonne. Gas turbines have what we call free steam, that's when they're first coming online, and that's the steam you make when you're generating just the electricity. You can see that's 0.55 of that value. The supplemental is 0.85 and it's 0.9, so you can see that's a very expensive way to go. That's the back end of the plant as a simulation. So here's the steam coming in from the gas turbines, here and here. And here's the various turbine sets. And what's happening in this model, I won't go into the detail of it, but just so you can appreciate. Simulators are normally based on feeds in, goes through the system, and then calculates what's coming out. I've put this on its head. What I'm doing with this is calculating what steam's required, and I'm back calculating through various functions to work out what the optimum gas demand should be, to see if they're using more gas than they should be. So it's a simulation in reverse, really. But you can do it, because in here you've got things like little calculators which will allow you to do things like that. This is just to show you basically the efficiency. This is the turbines now that are generating power. You see at low rates the efficiencies are shocking. Okay, so really you want to drive all this stuff at maximum if you can. Just as an example, they're doing steam from 45 to 10, but they're actually using steam at 4.5. But if you look at the one which is doing the turbine generator from 45 to 10, for 30 tonnes of steam, they're getting 2,000 kilowatts. If they go from 45 to 4.5, they get 3,000 for the same steam. So one obvious thing that could happen is they could perhaps, if it wasn't too expensive in terms of capital cost, take advantage of the fact that, and the thing is, the biggest steam demand is the lower pressure one as well, not the higher pressure one, which could force a decision on that. So the targets were basically as stated there. pretty self-evident, really, aren't they? But I think you probably gathered that it's a quite interactive plant, and the decisions the operator has to make in terms of which piece of equipment he brings online and at what stage he can bring equipment on. He can't bring turbines on at low demand rates. He has to sort of make decisions. So there's an awful lot of interaction taking place. So what this is all about is really trying to guide the operator to make the right operating decision. That's the report format. That's done in Excel. You probably can't read it too well, but there's a costing down here, which is basically telling him the cost of pounds per hour to run this facility. And at the moment, that's running at £398 an hour, £398 an hour. And obviously, if he's not running that efficiently, it took him some serious money through the year. That's an example of the various, so these are the various gas turbines. This is the alternator, these are the steam turbines, and these are the various costs. So at low demand, it's costing £141 an hour for 10,000 hours steam, and at £15,000 an hour, depending on which ones he's running, you see the change, 141 down to 11. I mean, if you take that over 6,000 hours, it's a lot of money, isn't it? And at £30,000 an hour, you can see he's starting exporting to grid. So he's actually he's making money now. He's running his process and he's exporting. And that's just another way of saying the same thing. So, the benefits from that, basically, in summary, these are the benefits you can get out of it. Yield isn't an issue on the thing we've been talking about, but energy optimization was. It helps in troubleshooting. It certainly increases the understanding of how to operate the process. It certainly optimizes usage of equipment. And something I'll touch on in the next example. But it allows you to predict unmeasurable parameters. Online analyzers, which I'm sure some of us have been involved in trying to keep those things going. If you get a good simulation, you can throw your online analyzer away. There's benefits for management as well in terms of increasing awareness of the plant. And particularly if your plant trends are changing in terms of reduction in demands, it helps you there. Do you want to ask me anything about that model, that approach? So in summary, really, we built a simulation to guide the operator in terms of how best to use the equipment on varying demand. This is the chlorine dioxide process. They had a major problem here because I haven't actually been involved with this process, but I do know they had serious problems with emissions to atmosphere. And they couldn't keep the analyzer working. And so it was costing them serious money. And the regulatory authorities were getting very annoyed with them. And this chlorine dioxide is, of course, is a worldwide usage for purified water. And what they did, they basically got a calibrated model that the regulators agreed with, and they could predict the emission to atmosphere, which was acceptable to the authorities. So they weren't measuring it, but they predicted what it was going to be based on the simulation. That's an example of the results. So this is results from the simulator, which are coming through in real time. The next one's interesting because this is the production report. This is data from SCADA, But if you look at the calculated values from simulation, he's got a section called process surveillance. And what he's doing is looking at heat exchangers. He's seeing how his heat exchangers are fouling. Looking at his compressor efficiencies. And he's predicting his emission to atmosphere, which has been accepted by the authorities. Serious payback on that. But he's also predicting physical property data, and he's also got some fault diagnostics going on. It's really in the ingenuity of the person who's applying it, in terms of what you can do with the technique. So that was the benefits that came from that particular process. I actually was in the office when he did that. This was about 10 years ago. I couldn't believe it. He was just sat there and just dialed in to somewhere in South America, and oh, that compressor's not working properly. I'll have to have a word with them about that. And we're talking massive compressors, some serious energy being spent. And he just dialed around. It's quite impressive when you see it. It's not very good for the simulator manufacturers, because he was just using one license to access about 5 plants. This is just a little add-on here, but we try to get people interested in training simulators. There's a lot of people in the industry doing training simulators, but we never had any success convincing anybody of the benefits of it. But a good training simulator on a continuous process plant must be worth its weight in gold. Right, that's the online simulation side of it. So we just have a little look at risk assessment. It's something that's really come to me quite recently in terms of things we've been getting involved with. I just put that up as a general intro. I'm sure we've all been into HAZOPs, where we look at various deviations of process and see what the consequences are of these deviations and what mitigations we apply. We were asked to do look at a system where they want to create hot water for to wash down equipment on a plant, and they were putting a heat exchanger in the flue gas of a boiler, and they wanted to make sure that this tank wouldn't overheat. So basically what we have, we've got a boiler system, superheater, boiler economizer, water heater, and then what we set up was a pump around the loop around that heater, and then we set a secondary loop up around the heat exchanger which did the hot water, and then the hot water goes to the plant. Quite interactive actually, because if you think about it, this temperature here can vary up from about 160 to 220, and if the economizer for some reason suddenly went out of sync, you could hit this with some quite high temperatures. So it was quite important that we protected this tank. So that was the challenge. That was the design objectives. I'm not going to read it out, you can read it yourselves. That's the simulation of the actual boiler system itself. So there's the boiler, the burner, superheater, boiler, economizer, water heater. So I had to do that first just to see what the challenges were on this hot gas side. So that's a typical simulation setup. This is the flue gas temperature dropping as it goes through the boiler. So this is the economizer heating up. This is the steam generation, constant temperature, and then there's the superheat. They're typical temperatures of the system. So you can see what we were up against here, 130 to 221. I mean, this was going to see this, but this mustn't see it. And the maximum demand here was 10,000 kilograms an hour. So basically, as this came off, we were making up water in this tank with cold water from the town. So we're doing level control on the tank. So there was an interaction with the cold water coming into the tank and coming directly into the loop. So it was quite a little challenge, really. So the answer was, that's basically the control loop. Three-way valve, as represented in the simulation by two control valves here, calibrated to represent that. Into one heat exchanger, which was preheating water to a boiler, and this is the water heater here. And we have the valves in split range, as shown there. So we can set that up in the simulation. I can, as I said earlier on, I can run these simulations afterwards for any of you who are interested in seeing them. Just a quick reminder of control valves. In the simulator, we can take care of all the characteristics and sizings and things, and it's absolutely fantastic for checking sizings of valves, the effective characteristics on valves, control the tuning. But that's not new to anybody in the room, I think. And then we can do controllers as well, so we can do PID settings. We can set the calibration of the controller to match exactly what's going on the plant. That's the basic algorithm that I just put in as an example.
Well, presumably you can determine if the process is inherently unstable and
yeah.
It can't be tuned.
Yes, it's brilliant for that. Yeah. I mean, I feel quite. I think I'm sure universities are using it, but I think of my control course at university. With something like this, it would really teach them how to tune controllers for different processes. It's a fantastic teaching tool, and I can only hope they're using it. I'm not sure they are. That's the simplified process flow diagram. So basically we have a pressurized water loop here. There's the flue gas. So this self-compensates itself because it's sealed and it automatically pressure pads itself. So if it goes above boiling point, it increases the pressure here. So there's no boiling taking place in this loop. There's flashing taking place in this drum, but it's not taking place anywhere else. So we're pumping around there by these valves, and then back again. And then the cold water side of it is this one. There's the makeup water on level control. And then we come through here into that heat exchanger. We're doing temperature control on these two valves, and then we've got protection there. So that's what we could do, and that's what we have now. That's just the parameters for the simulation alarms. That bottom bit might be of more interest to you than the actual process conditions. This is quite a new feature within this simulator. We can create what we call an action matrix. So basically, this is a dynamic simulation. I can bring the dynamic time into this. This is Excel. The dynamic time into here, and let's say the dynamic time was at 240. what Excel does is inject these values into that row, okay, which then drives the simulation. So what I've set up here is a matrix of values that are going to be fed into the simulation at various times. So you can see I've, at 1500 minutes, I'm changing the flue gas temperature to 221 from 160. So I'm doing a step change to see how the control system responds. I haven't started this is the deeming water demand. There's no demand to begin with. Then I started at 9,000. Yeah, that's the deeming water demand. This is the wash water demand here. These are the circulation routes, so I can play with those values. I've left them at constant. But I can also fail valves. So what I'm showing here is, just by injecting certain parameters in here, I can make the valve that is normally fail closed, I can make it fail open just to see what happens. It's just jammed open. And I've done that for 6 hours. You'll see what that looks like on the response. Very powerful. So you come out of a HAZOP and say, well, I'm not too confident about your control system, and you can show the demands on the control system and see how it responds. So what we have here is the temperature we're interested in is this blue. That's the wash water tank. Okay, you can see it's pretty stable. And the circulating loop, that's it there. So you can see how it's pretty good, isn't it? And that's the demands we're putting onto it. That's the water coming round from the pressurised water side. The client was well impressed with that. That was a test. What happens if the economizer suddenly kicks off? All of a sudden we get this kick in temperature here, but again you can see that the tank temperature is pretty stable. So it's showing that the control loop, provided everything's working fine, is quite responsive. I failed the valve open now, so what we have, this is the control valve position to the heat exchanger. This is under normal control here, and there's no load on the system now, the tank's up to temperature. But then I kicked it wide open, I forced it open, and you can see that's the loop, wash water loop temperature. It peaked at 100. I had a bit of a shock when I did this, to be honest with you, because I was running the tank at 50% level, and I was circulating at 40,000 kilograms an hour, and I was a bit shocked to see it got up to 95 degrees C in the tank after 6 hours. So there's an example of the what-if scenario. Okay, I mean the chances of a valve failing forced open for 6 hours is pretty unlikely, because there's going to be additional protection in mitigation to that situation, but that sort of gives you an example of how you can look at a process and see the worst case. So what I did, I changed the circulation rate and increased the level to 90%, and you see it peaked at 84. So it had the effect you'd expect. But imagine trying to do that before you had a simulator. So that's the hot water one. This is the last one. Distillation column. Typical distillation column. Vertical recirculation, natural recirculation reboiler. Steam. Feed. The steam is ratioed to the feed. That's done in Excel. So I can make this simulation talk to Excel, so I can control it from Excel. These are little modules to change feeds, they're little ramps that we can use to change values. The bottom of the column's on level control, which is this fella here. The overhead, this is the relief route, if we get overpressure in the column. And this is the condenser route into reflux drum. I'm monitoring the composition here, and I'm actually taking a thing out of Shinsky's book just to mention him. I'm adjusting the distillate set point based on the feed flow and the composition of the feed, composition of the bottom, and the composition of the top. I've written that up a little bit in there, so just to give you background. The bottom line of this is you can't do a control system without, you can't transgress the mass balance or energy balances in a piece of equipment. The control system has got to comply with that. I mean, what you do see a lot is level control on here and level control on the reflux drum. Nightmare to control, because what you're basically saying is you're controlling the mass balance at both ends, and you can't do that. So what's decided from the feed and the operation is the distillate takeoff rate, and then the reflux flow is dependent upon the boil-up rate and the distillate takeoff. So what I'm going to do, I'm going to force the pressure up now in the column, and at the same time I'm forcing the pressure up in here to the relief point. So what's happening is as the pressure is going up, this is the reboiler duty here. The temperature is going up in the bottom now because the pressure is increasing, which means the temperature difference across the heat exchanger is reducing. So the amount of heat going into the column is going down, as shown here. And there's the reboiler temperature difference there. And what this shows you, I mean, the traditional way of sizing relief valves on columns is to take the perceived maximum heat input to the reboiler based on its area and heat transfer coefficient. You take a latent heat, which could even be the feed latent heat, but wouldn't be very realistic. What you try and do is take the latent heat of the top tray at relief conditions, but I don't know how many people know what the composition of the top tray is at relief conditions. It's difficult to predict without a simulator. So basically you tend to oversize the relief valve with the conventional one. But what this is showing is the vapor coming into the condenser. We're now increasing the temperature, so the boil-up rate's dropping, the reflux rate's dropping. This is the overhead vapor. It's hiding behind the green one there, and then it joins back up again. And then the relief valve lifts here. Look at that, 5,500 kilograms an hour. Your design would probably have been based on something like 16,000 kilograms an hour. But what that's telling you is that the simulation is predicting a much lower value. And it's actually telling you what's happening. So once the relief valve reseats, then this tells you about the recovery within the column. See, it's taking quite a while to get back again. I've controlled the lift and the reseat, so it's not a true practical representation of what would happen, because the relief valve is very large. It would just lift and then reseat again once it had knocked some of the pressure off. And I think the interesting bit here is for the maximum duty of that's the relief load. Relief, that's without drink as well. Relief load, 35,000. The duty at relief is that, which is 24,000. And yet the simulation's predicting 6. I'm not saying I would size the relief valve at 6, but it would certainly start me thinking about the difference between an 8-inch relief valve and a 6-inch relief valve and a 4-inch relief valve with some confidence. that would need a 3-inch relief valve. That needs a 6-inch, and that needs a 6-inch. A different trim. So I think the benefits. I think hopefully I've demonstrated what potential benefits are available. And that's just a little summary, really. That's the last slide.
Well, when you're coming up with things like relief valve sizing, presumably it requires a lot of confidence. How is that confidence validated?
Well, that's why I said at the end. I wouldn't necessarily size it to the 6 things, but I think I would say it depends on the process. As you probably are well aware, that if you oversize your relief valve, that can cause you serious problems as well, because you can lift trays, you can create a massive problem on the column. I mean, I know some people. What I would be inclined to do is have a first relief valve set at the lower figure, and then I'd back it up with another one.
Yeah.
I wouldn't like to put my reputation on the whole thing, but I think what it is indicating is that with dynamic simulation, it opens your eyes a little bit to what is really happening. You can imagine what's happening because you know that the temperature's going up in the column, and obviously the heat going in is going to go down. But it's hard to put a handle on it without spending a lot of time.
What sort of time's involved, John, in setting up a system like one of these typical systems that you've been showing us?
It depends. I've spent hours sometimes. Like the distillation column, I've probably spent about 2 or 3 days on that.
Right.
But it depends. I mean, like the water system, probably a day to come up with the concept. I mean, the concept was the first thing, and then how you go from there in terms of the control loops and tuning and all the rest of it. But I'd say generally 2 weeks probably for a project of something like that.
How sensitive, if you're doing it in Excel, how sensitive are the results to sort of the time difference interval?
You can adjust the step time within the simulation down to seconds. So, for example, you could look at, say, a relief manifold, and you could actually look at the onset of two-phase flow in the relief manifold down to seconds. So there's no restriction down to the sort of second value. The trick is to make sure you get the right step time.
That's what I was thinking.
Yeah.
Because in ordinary simulations, if you get the wrong step time, your simulation can be a load of rubbish.
Yeah, very much so. And if I didn't mention it, but if your thermodynamics, you know how materials are interacting with each other are not right, then it's rubbish as well. I was quite surprised. The refinery industry, the basic thermodynamics in the refinery industry, it tends to be quite straightforward. You know, I thought it would be complex. I'm talking about distillation columns and the crudes.
So is this, when you build these models, is it built up of function blocks? You've got a block for heat exchanger.
Yeah, just typically a graphic block.
Yeah.
And within the graphic block is all the various parameters, and you can set up how you want. You can set up heat transfer coefficient in an area, or you can set up a target outlet temperature. You can set up delta T's across the thing. You know, you've got complete flexibility on that. Okay.
Excellent.
Yeah. Thank you. If anybody wants to see any simulations, I'm more than happy to run them through.
How long do they last? Is it?
Simulations?
Yeah.
Not long.
Right. Is it worth us seeing an example for people interested?
Yeah, if you want to. Phil, will you set up the... That's the wash water system. And just to sort of give you an idea, unfortunately we cut off a little bit there, but I'll just double click on it. So that's the specification for the pump. So you can do pressure increase. Useful things like this, if you're looking at networks and things, you can look at net positive suction heads available. It tells you calculated powers. And the thing is, you can extract this information and stick it in Excel, and you could work out power consumption for a total facility from the simulation. This is the wash water tank. This is a dynamic tank, so we've got the physical dimensions of the tank in. We can play around with different types of heads. We can do initial level to start off with, and we can specify the conditions of the inlets and the outlets. So that's where I played with this circulation rate, which is in fact I'm telling it what the flow out here should be. That's another pump. This is a pipe, so we can size the piping, single phase flow. But you've got a whole range of options in terms of what you want to check. And then you can actually stick in different valves and fittings. So you can do a rigorous analysis of the pipe system. Control valve. So it's the CV of 50, rangeability 50, equal percentage. And I tell it what controller it's going to talk to. It gives me the valve position, and it actually gives me the calculated values. All these values, again, are available to you, either in Excel or through OPC up to the SCADA display. So you really can mine into a lot of data. The controller. It did that because I put the text in there. Let's click on the text. So there's the controller. I've got a set point of 60 on it, and I've calibrated it from 10 degrees C to 100 degrees C for a 4 to 20 milliamp input. There's the controller action. So it's reverse action, and it's telling you the control valve, and it's actually telling you what it's measuring. So in this case it's measuring stream 12 temperature. It actually could measure any stream in the flow sheet. It doesn't. Its position in the flow sheet isn't like our real control groups. I could select anything to control that. I could change that to composition. I could change it to flow. The heat exchangers, I've actually set up, based on the knowledge of the heat exchangers, the heat transfer area and the heat transfer coefficient. We could actually put a real heat exchanger in there, based on a shell and tube heat exchanger. Alternatively, if it's a special, I actually mention, no, I don't mention it in there, but we use plate and shell heat exchangers quite a lot, and the manufacturer won't release the data to us, but what he did was give me a matrix of temperatures and flows with heat transfer coefficients. So what I could do is feed the flow and the temperature into Excel, go and look into the matrix and extract the heat transfer coefficients and feed it back into the simulation. It's really powerful in terms of the various techniques you can apply. And that's the flue gas there. And this is
just thinking about that then, John, at first sight, that on the heat exchanger there looked like a fixed variable. When you had that heat exchanger up there and the heat transfer coefficient,
yes,
it looks like a fixed value there.
It is.
But what you're saying is you can actually arrange for it to be
variable.
Variable.
Yeah.
But if I put a real heat exchanger in there, it'll vary it itself as well. You might be asking me how confident I am about that heat transfer coefficient. I know I've got constant flow on the shell side. I know I've got constant flow on the tube side. I'm not manipulating the flows,
Right.
so I can be confident of that
Yeah.
coefficient. This is that's a mixer, and that's a divider. So you can actually, that divider has got that value in there from the control valve, because the control valve calculates the flow in the loop, and it has to tell. There's two control valves talking to this divider, and based on the control valve position, it tells the divider what flow to go down its leg, so they interact with each other. And it's connected to a spreadsheet, and you can see what I'm doing in here. I'm sending the dynamic time into cell A2, and then I'm sending these values back to ChemCAD. So stream 18 temperatures going into cell B2, stream 14 C2, unit up liquid flow spec. So there's the matrix that's going to control things, and you can. I hope you can see the potential benefit in a HAZOP situation where you've been challenged with various things. You could actually set this matrix up to sort of really respond to challenges that are coming out of HAZOP. I'm going to, I'll just run. So what we're looking at, this is the water demand to plant. This is the temperature in the tank, and this is the pressure. This is the temperature in the loop, and this is the flue gas temperature. So here's the flue gas temperature. That's the temperature in the secondary loop. You see it's settled down at 60 now. The tank is heating up from cold. I mean, even just to do the calculation of how long it takes to heat the tank up from cold to 60 is a nightmare. But you can see it's taken 10 hours. So that's something in production interesting. How long is it going to take me to get me water up to temperature? Now there's the water demand gone on. That's the water demand from plant now at 10,000. You can see it's kicked that a little bit. There's also level control going on here as well, which I'm not showing you, but there's cold water going into the loop as well. That's what's happened here. The level's gone down and we're injecting cold water. That's why it's gone down. But it's not had any effect on the tank here. This is the flue gas temperature changing. Actually, I've been very unkind because what I did, I failed the valve open at the same time as I hit it with the change in flue gas up to the maximum. So I probably wouldn't hit that 86 degrees C I showed you on the presentation. Imagine how long that would have taken with a 60s computer. I think you'd come back 2 days later.
So what are the peaks on stream 17 then?
17 for which is that?
Which is the one on
Bottom left.
bottom left.
But, well, if you read, it's 10,000. It's just in the calculations. Doesn't mean anything. That's 10,000. That's 10,000. It's something in. I don't know what it is, to be honest with you. Why did you ask that question? I told you not to ask
I
anything.
just wondered what the peaks were, John.
You can see some similar peaks
Yeah, you
occurring.
can see them on the other side.
Yeah. I think there may be real There's some variation going on in there as well, but again, that's down to step times. I could get rid of those. What I can do is change the step time within a simulation, so I can say from 0 to 1000, I can have a 5-minute step time. But when the relief valve lifts, I can change it to 5 seconds. So for that section where the relief valve's listed, you can shorten it. Okay. So that's that one. And then you can navigate the model and look at various things. So you can see what you can look at in here then. All those properties are available to look at. It just could be that you're interested in the viscosity. So the simulation is opening up a whole world to you that wasn't available to you using our, from my days we used to measure specific gravity, viscosity if we could, and composition, but we could never, well, Mr. Ransom could never keep the composition on as it's working, could you? But at Roman Haas, where I started in this area, we had chromatographic analyzers. It was a nightmare trying to keep those going. I had 2 blokes full time on each one.
You could still couldn't control the smell, could you?
Hey! That was unkind for that will cost you fines. Okay, so that's that one.
He was an instrument engineer then, he wasn't a process engineer, chemical engineer at the time.
Is there anything else you want to see on that one? I'll show you the distillation column if you want. But the trick is in this, how you set this up. I'll show you this one because as instrument engineers, I find this one quite interesting. You've probably seen many times where people try and control temperature coming out of a heat exchanger by manipulating the cooling water flow on the other side, and it's a nightmare because you've got all the dead times of the heat exchanger, and so this one's just set up to the control valves are set up as before, and we can change these constants to make them work the way we want to work. And basically it's just a simple control loop of that's it finished. But you can play with that and demonstrate sort of heat control, transfer control over heat exchangers. I'll just show you this one. It's quite addictive, to be honest with you, when you start working with it.
You run training courses for it?
Yeah. I go all over the place. It's great. Dynamics isn't very well taken up though. Very few people use dynamics. I think the problem is with dynamics is they need to have the instrumentation background as well as the process, and I think that's what is the resistance to it. BP use dynamics a lot, I know that. So that's the one I showed you. I'll just show you the column, you haven't seen the column. But you can set the pressures, you can set numbers of stages for the various things, you can set up what type of model you want to run. You can have pack column, tray columns, you can have reactive distillation. And this is set up for dynamic distillation, so I've set it up for steady state continuous, but you could actually start up the column from a dry column. And I'm ignoring hold-ups, so I'm trying to keep it simple. What I'm doing here is that Shinsky control model of calculating the distillate flow, and I'm doing all this in Excel. So the blue cells are what's coming out of ChemCAD, and the red cells are what's being used in the calculation to create the set point. And these, you haven't seen these, but if you like, I could combine all these ramps into that action matrix that you saw before. But when you're trying to do coincident things and do phasing, it becomes a bit difficult if you've got 10 of those on the flow sheet. But so we can set these ramps on individual things. So that's me changing the pressure on the column. So at 960 it's 1.5, and then it's ramping up to 4.1. But for the simulation to work, I've got to do the same thing in the reflux drum. That's the same as before, you've seen that. And I've just put this in. I'm actually introducing fouling here. So what I'm actually saying is the subcooling due to heat exchanger fouling is changing, just to demonstrate the fact that that's available. I know one company who's developed some really complex interfaces to predict fouling in heat exchanger chains on a big plant. But they're using VBA. There's a VBA interface with this as well that you can use to develop things. So off we go. What we're doing. This is the subcooling on heat exchangers. This is the relief line here. This is the vapor load from the top of the column. There's the heat exchange, the condenser's fouling here. This is the reflux flow. That's the overhead flow. When you start to see these dropping, that's when the pressure ramp is start to come in. So it's nice. There's the column pressure building up now. So the overhead flow has dropped off. There's the relief valve lifted. Now it's going to reseat. And then the column's going to start to recover. That is not the... And that's the end of the simulation. That isn't real life, that. The lifting this, I've controlled that. I'll just show you this column because you asked the question earlier on. I set in run times. You see I've set 2019, add 5 minutes, step size. When the relief valve lifted, I took it down to 0.33 of a minute. Right. From memories, I can't remember what that is, but it's 15 seconds or something. And then after that, I raised it back up to 5 minutes again. So you can actually change the step size at points in the simulation. Okay.
Yeah. Right.
thank you with the tie first of all, John.
great.
You have a large number of them, and we're very pleased if you take one off us.
Okay, thank you very much
Right,
indeed.
I'd
Appreciate that.
Right, just like to thank you for
Okay, thank you.
a very interesting talk. Yeah,
Okay,
I'm sure
yeah.
it's given quite a few people food for thought. If I can just ask us to thank you in the usual way. We will be going across to the Star after this, so anyone
Is that,
who
is that one that way? Or is that,
right,
Southfield
it's
Road.
the one across
Oh,
straight across Southfield Road.
is
Yeah.
that the one we got thrown out of?